All right. So energy, oh, I'll make it so you can see it. Energy on a large scale. And we said previously in this course, but we also said in grade 11, that when we're talking about force due to gravity, well, really in general about force due to gravity, not just about on large scales, but in general about force due to gravity, mass 1 times mass 2 over the distance between those two centers of mass squared times the universal gravitational constant, 6.67 times 10 to the power of negative 11 Newton meter squared per kilogram squared. That's going to give you the force of attraction, the mutual force of attraction between those two bodies. Okay? And the bodies might be a large body and a small body, and that's why in my childhood physics textbook, we used big M's and little m's. In general, you don't have to use big M's and little m's. Really, it's just M1 and M2. Okay? So we've got M1 and M2, a distance r apart, and I just like big M and little m just to emphasize that I like big M to be the planet and little m to be the satellite. Okay? And then just yesterday, we said that gravitational potential energy between those two masses was equal to g m1 m2 over r. Not r squared, but just over r. So we've got an FG calculation and we have an EG calculation. Yep.
I thought it was negative.
Oh, negative. Thank you very much. How can I make that look nice? Negative. Okay. Now, I want to make a proposal. I want to say that, look, if this little satellite here, we're calling M2, is a moon, or any kind of satellite, could be a natural satellite, could be a man-made satellite, but let's say that it's a moon. I know that the force of attraction between the moon and, let's say that big M is Earth, is going to be Fg. But I also know that that Fg is going to be equal to the centripetal force. Because is there any other force that's keeping this moon in orbit other than Fg? Shouldn't think so, right? Like unless there's somebody that's been tying a string to the moon, right? Like there's not a tension force, not like in that little experiment that we did. There's not some tension force that's holding the moon to Earth. I guess you could do it. You could get a great big chain and chain the moon to Earth. That'd be weird. But that's not the way it works, right? The only force that's keeping these two things bound together is gravity. So what I can do is expand these two formulae. I can say Fg is g m1 m2 over r squared. And I could say that Fc is mv squared over r. Remember that old formula? Fc is equal to mv squared over r? We did that back in the dynamics unit. Okay. Now the catch is I've got three m's. But two of these m's are the same m. Do you remember when we were doing the dynamics unit, we might have had an object orbiting around a central point. And the central point may well have had a mass at it. But if the object was rotating around a central point, and that's where we developed this mv squared over r equation from, which m is this? Is this m1 or m2? Yeah. M2, yeah. So you know what, let's just put it in there as m2. Just to clarify, because we've got too many m's on the page. Yep.
For when the masses are like really big and really similar in size,
Yep.
and they're orbiting around each other, wouldn't the radius be not the same?
Well, if the masses are of a comparable size, they actually orbit around a central point between the two masses.
So for the triple force, wouldn't the circle be smaller?
Well, let me sketch out what I think you're talking about, because I think you're onto something. Actually, you know what? Let me finish this derivation, and then I'll come back to it. Okay, I promise. All right. So if we have an m2 on both sides, we can divide both sides by m2, because they're both monomials. They're not binomials or anything like that. So I can just divide both sides by m2, no problem. And then I've got an r squared on the bottom here and an r on the bottom here. So I could multiply both sides by r, which would eliminate this r and eliminate this squared. Okay. And now I haven't really told you what the object of this might be, but what I might want to know is the orbital velocity for a planetary system, the average orbital velocity. Let's just call it v average. That's the v that we have right here. Okay? So really, I've eliminated the m2. I've eliminated r. All I really have to do is square root the left-hand side and square root the right-hand side. And what I get is v equals g m1 over r, all square rooted.